Pleasure to introduce Joshua Jackson from the University of Cambridge, who's talking about getting a Harder-Narasimhan theory to classify similar trips.
Thanks. It's nice to be back here. So I'm giving two talks this week on the same topic, and one of them is here at the University of Essex, and on Thursday I'm giving a similar, but not the same talk at the University of Essen in Germany. So I'm working through all European universities in, I guess, reverse alphabetical order. Okay. Yeah, so this project actually goes back quite a long way, and it's nice that Francis is here because this goes back to when I was a PhD student, and I used to meet Francis once a week, and we would have in the early stages sort of discuss mathematical ideas and things. And I remember once I went into her office and she said, I was thinking about that idea that you had last week about Harder-Narasimhan theory for curves, and I think that's a really good idea, and you should work on that. And I had absolutely no recollection of this idea, but I must have said it at some point. So I want to get the theorem out of the way because the theorem is sort of technical, and then I'll spend the rest of the time trying to explain what the point of it is. Can we maybe want to get rid of this super thing? It's in the way. That's better. Okay. So this is joint work with Dave Swinarski, who's at Fordham University in New York. And okay, so it says if you have a monomial curve, then some point in some Chow variety has an asymptotic worst co-character as d tends to infinity, where d is the degree of the curve. So probably this will mean nothing to most of the people in this room. I'll spend the rest of the talk explaining what this means and why one should care. And then the second part of the theorem says that the same thing is true for any rational curve with one unibranch singularity. So depending on whether you like even or odd dimensions, you can either visualize it as a kind of bubble with a pinch bit, or you could think of it as this kind of y squared equals x cubed thing. And in the interest of honesty, there's an asterisk here. This is under some technical assumptions which we expect to remove. I will not tell you what the technical assumptions are.
So that's monomial.
Monomial means, well, I'll tell you later, but I can tell you now. It means that you take a parameterization, which is just powers of t. So 1 comma p to the whatever comma,
So look at these two.
Sorry?
So it's rational.
Yeah, they look like this.
Yeah.
Okay. Right, so what's the motivation here? The idea is to find an algebraic variety parameterizing all. This is going to be really annoying. That stuff in the way. What do I do about this?
Yeah, you can definitely.
How do I get rid of this? Does anybody know? Beautiful.
Magic.
Yeah, it can hear me. Okay. Right, so we want to understand projective algebraic curves up to isomorphism. And for those of you that don't know, in algebraic geometry, classification questions have continuous answers, right? We've heard about moduli spaces today already. So why is this not a trivial thing to do? Well, here's the classic example. You consider this family of curves. So this is the equation, and there's a parameter here, t, and that's some complex number down here. So I can think of this family of curves as for each t, I have a kind of fiber here, which is the curve living over that complex number. And if I have t non-zero, then you can see from the way I've drawn it, these curves are all the same. But when we hit t equals 0, something bad happens. We introduce a cuspidal singularity. So this one is not like the others. So why is that a problem? Well, if you think about we had say a topological space parameterizing these things, it would have to be very non-separated or non-Hausdorff, if you like, because somehow we'd have a point which would correspond to this curve here. We'd have a point which would correspond to this cuspidal guy at t equals 0, but somehow this thing has to be infinitely close to this thing. This guy has to sort of lie in the closure, right? Because these curves are all the same curve, and then this cuspidal one is different. So if we want a nice space parameterizing these things, well, these two just don't play well together. So if things don't play well together, you have to break the problem up, right? So you break the problem up into pieces. You make sure that this guy is in a separate piece from this guy, and that will hopefully mean that, okay, you're not going to have one thing which parameterizes all curves, but you'll have maybe a few things that will parameterize curves that play nicely with each other. So, the basic question is, how does one actually do this? How do you know how to break the problem up so that you can get a nice space? And in some sense, that's what all of this is in aid of. How do we break this problem up? Okay, so I want to, because this is an audience, probably, I don't know, maybe at least half not algebraic geometers, to keep things as simple as possible. So let's just think about plane curves, right? So I've got a curve C in P2. So it's the vanishing of a homogeneous polynomial in X, Y, and Z. It's of degree D. D is the homogeneous degree of the polynomial. Okay, so such things are, they correspond to points in this space, right? I just write down what f is, and that gives me a degree D polynomial. I projectivize that because scaling the polynomial doesn't change the vanishing locus. And here is a nice space that parameterizes these things. But we want it up to isomorphism, right? If two curves are isomorphic, we want them to be the same point in the space. So we have this automorphism action on P2, which induces in turn an action on this. And if they're in the same orbit, they're isomorphic, so we want a quotient space. So this is the idea of GIT, which we've heard about already today, fortunately for me. But if you just take the topological quotient, this is not going to be nice, for the same reason that we saw before with the family of curves degenerating into the hospital one. So again, you have to split the problem up. And one of the, I guess, selling points of Mumford's geometric invariant theory is if you have a reductive group acting on a projective variety and it's acting linearly, meaning that it's a representation, G into GLV, which is inducing the action on your projective variety, then you get a nice projective quotient variety, not of X, but of some open locus, which is called the semi-stable locus. So you don't get a quotient of all of it, because if you did that, you get something that wasn't nice, but it picks out for you a nice open, which does have a quotient, which is nicely well behaved. Double slash notation is just the GIT quotient. If you're not familiar with it, you can just think of this as the topological quotient for the whole talk, and you won't really miss anything. Okay, so GIT picks out this open subset for us, and this open subset has a quotient, and it's defined in this way. So you're semi-stable if there is some G-invariant polynomial constant, which does not vanish at that point. So it's defined in terms of invariance, right? Invariant polynomials, hence geometric invariant theory. Okay, but to actually compute this semi-stable locus of principle, one would need to compute all of the invariants. So you need to know a complete list or a generating set of all of the G-invariant polynomials. And in general, this is going to be kind of hard, or at the very least annoying. But it sort of came out of 19th century invariant theory, right? People like Hilbert were very interested in computing these invariant functions. But at some point, they just stopped. I think because it got too hard and they didn't have computers. So you don't really want to do it this way. Okay, so how do you actually compute this semi-stable locus? Well, the idea is you use representation theory. So basically, what geometric invariant theory is using representation to make life easier. So how? It's a short talk, so I'm only going to focus on the case of the torus. If you replace T with a reductive group and you say up to conjugacy everywhere, then this stays true, but let's just stick with the torus. Okay, so I have a torus acting on a projective variety linearly. So there's a representation V of this torus, which is like GM to some power, or C star to some power, if you like. So this has some weights, and they live in this Lie algebra of the torus. And so I can draw a picture in this vector space where I have a vertex for each of these alpha i's, and then I can just sort of connect them up into the convex hull. And if I have a point of my projective variety, then okay, it has some coordinates. I can look at which of these xi are non-zero, because I've diagonalized the action. Each of these xi's is going to be a weight vector, so it has a corresponding alpha I. So for my point, I can just take take all the xi's that are not zero, take their alpha i's, and take the convex hull. Okay, so this gives me a convex polytope associated to a point, which is going to live inside this vector space. So every point of x has its own little, they call it state polytope, which is just a convex polytope inside of vector space. Okay, why would I want to do that? The reason is that the point x is semi-stable if and only if the origin is inside this polytope. So there's a kind of, you start off with some kind of invariant theory, algebraic geometry thing. You then use rep theory to reduce it to a sort of convex geometry type question. Here's a polytope, does it contain the origin? And it's actually, in the case of toroid, pretty easy to see why this would be true. The substance of this is when you have a more general reduction against. Okay, so let's go back to plane curves. So for plane cubic, y squared z equals x cubed. The state polytope looks kind of like this. I've got, z cubed, y cubed, and x cubed. So I've got all the monomials of degree 3 in these variables. And then, okay, here I've got two monomials which occur with non-zero coefficients. So I get x cubed, that alpha I appears, and I get y squared z, which is here. And so here are my two weights that are appearing in the state polytope of this curve, and the convex hull is just the line segment that joins them. So you can see here, because this doesn't contain the origin, this is unstable, according to what I've said here. All right. So classical GIT, if you can set up your taxonomic, your moduli question as a question of finding a group action, for the semi-stable locus, which is almost everything, gives you a quotient, and it tells you, using this kind of criterion, how you compute which things are semi-stable. Now, what I want to do is not stop there. I want to work out things which are not semi-stable, which are confusingly called unstable. And roughly this will correspond to singular curves, roughly. It's curves with bad singularities. So the first thing we need is to turn this from a kind of binary yes, no, you're either semi-stable or you're not thing, into something a little bit more quantitative. So the way this has been set up, the obvious way to quantify the failure of semi-stability is to ask, okay, well, if the origin is not on this polytope, then how close is it to the polytope? Now, this of course requires me to have a notion of distance in this vector space. So technically I need an inner product, and if it's a reductive group, I need an invariant inner product, but I'm not going to worry about that because I've not got time. Okay, so the problem then is you're given some polytope and some vector space, and you're looking for the vector that lies on that polytope that's the closest to the origin, so minimum norm with respect to whatever inner product you've chosen. Equivalently, you can think of this in terms of finding the direction in this vector space which points to the closest point. So direction corresponds to a co-character. If you take the kind of infinitesimal version of this will be an arrow that points in some direction, and the point where it first meets the polytope, you're looking for the lambda such that this is the closest point. So you're minimizing, actually maximizing this function. So you're looking for, if you like representation theory, you can say, well, this co-character allows me to restrict the torus representation to GM. I get a representation of GM, so the weights are just going to be a bunch of, numbers. Here they are, that's how you find them. And the smallest one is how far along the arrow you are. And then of course you have to normalize, because if you scale this vector, that's going to result in a bigger number. So you have to normalize it, otherwise you're not going to have a max. So the point of this is to say that equivalently, you're looking for a co-character that maximizes a certain function. That's equivalent to finding the closest point that lies on this convex hull. And we call these worst co-characters, or I call them worst co-characters. You could call them Kempf co-characters, because Kempf was the one who really sort of started thinking about these in a systematic way. Indeed, Kempf proved that if you take a reductive group, these worst co-characters exist. You always can find a maximizer, and they're unique as much as they can be unique. They're unique up to conjugation by some group, blah, 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 but they're essentially unique. So it makes sense to look for these because they always exist and are basically unique. Okay, so this gives us a way to measure instability, right? You can, given a reductive group acting on a projective variety, you can split it up into a stratification where you index each point according to its worst co-character. So this, it's not obvious, but this gives you a G-invariant locally closed stratification of X. Sometimes people call this the Hesselink-Kempf-Kerwin-Ness stratification. It goes by other names. I'll call it the instability stratification because it's slightly shorter. And we've seen this problem in one of the talks earlier. There was this problem about classifying points on, well, here I've done P1, but moduli of points. You could take n points on P1 up to automorphism of P1 and ask what's the instability stratification there. The semi-stability condition turns out to mean that you can't have half your points coinciding. And as you'd expect, the other strata, the unstable strata, are saying, well, how many points do coincide? So I suppose this little example here in blue is meant to say, well, at least for this one, if you guess what you think the appropriate measure of instability is, that is indeed what the GIT tells you it is. So this gives you something which is geometrically plausible, at least in this example. And what we want to do is compute this instability stratification for curves. That's the idea. Oh yeah, and then just at the bottom here, I did some stuff with Vicky Hoskins, which is basically just building on an idea of Francis, which is sort of moduli spaces of unstable objects. So the idea is if you can understand this instability stratification, you can quotient these unstable strata, and then you can get moduli spaces that parameterize things which are not semi-stable, so things that are left out of the standard classifications. And for technical reasons I won't get into, you need non-reductive GIT to do this. And this is one of the main, to my mind, one of the main selling points of non-reductive GIT. That even if you start with a reductive group, you sort of have to care about non-reductive groups if you want to classify everything. All right. Okay, so let's talk about curves. So for plane curves, recall we have this vector space of degree d monomials in x, y, and z. And if we projectivize that, that gives us a space such that points will correspond to curves embedded in the plane. And so we can ask what's the semi-stable locus here? Remind you that's the open stratum that does have a quotient. So this is like the classical kind of moduli space, if you want. Okay, so smooth ones are always semi-stable. So that's good. So the GIT quotient here is a compactification of the space of smooth curves, plane curves. So you know you've got some open subset in here, which is, if you want to think about it this way, it's like a moduli space of compact Riemann surfaces in the plane, and together with some stuff on the boundary, which makes it the moduli space nice and projective, compactifies it. And you allow mild singularities. So if the singularities are too bad, you won't be semi-stable. But if they're mild, then you'll get away with it. So for example, I think I've done this right. For quartics degree 4, you're allowed things that sort of analytically look like y squared equals x cubed, like this, and ordinary nodes, things that analytically would just look like two lines crossing. Those are allowed. But if you have something worse than this, then you're not going to be allowed in this moduli space. You're going to get kicked out. Okay. But what about the instability stratification? So this is just the open stratum, right? What about all the other stuff? So there are two papers that I know about that compute the instability stratification of the plane curves. One of them is a paper of Francis and Ronnie Lee, is it? From a little while ago. And they were doing this for a completely different reason, is my understanding. They were interested in computing, as it says at the top, the cohomology of moduli spaces of, I guess, semi-stable K-free surfaces in some sense. Because you can think of these as a double cover branched over a sextic. But anyway, they look at, so these here, down here are the strata in the instability stratification, and there's various data here which they needed to compute the cohomology. And then the other one is more recent, and this is a quartics, so degree 4. And this one is a little bit more geometric because they were sort of interested in the geometry of what these curves actually look like. So here are all the different strata, and then down here you can see what geometry is allowed, what a generic member of that stratum looks like. So I guess that it doesn't really matter, you know, what if each of these lines says, but the point is there is a relationship between how bad the singularities of the curve are and which stratum you're in. And roughly speaking, the worse your singularities, the higher the stratum you're in. So this really is a kind of measure of the instability of the plane curve. It's a measure of how unstable the plane curve is. Okay, so that's plane curves, right? So I unfortunately do have to get a little bit more technical here, but let's just see how we go. So the point is, why do you need to think about curves that are not plane curves? The problem is, if you think about the sort of plane curves inside all algebraic curves, then the codimension of this inclusion to infinity is as g goes to infinity. So you miss almost everything if you only think about plane curves. So we do have to care about curves that are not. Okay, so that means we have to bring out one of the big important classifications from constructions rather from GIT. There is this very important space called MG bar, the moduli space of stable curves, which is some compactification of the MG space of smooth genus G curves and isomorphisms, so compact Riemann surfaces, if you like, of genus G. Okay, and there's a construction of this. If you're not a GIT person, don't worry what this means, but there is some way of embedding your curve into projective space, which leaves you with a locus inside something called a Chow variety, which parameterizes these curves. This Chow variety is acted on by the, well, I've written GLM plus one, but it's really the automorphism group of this PN, just change of coordinates in the same way as for plane curves, and then MG bar, this classical quotient is the GIT quotient that you get. So the takeaway from this is there is some GIT construction which allows curves that are not plane curves, which in some sense reduces to the plane case if you make it simpler. So what we want to do is understand the stratification that this gives us. That's the point. So we can classify all singular curves, not just the planar ones. Okay. So what does semi-stability mean? Like, what's the open stratum in this here? Well, you are only allowed nodes, so you can be smooth, but you can have singularities as long as they're nodes, and your automorphism group has to be finite. So again, just like in the planar case, there's some relationship between being in the open semi-stable stratum and having geometry that's sort of not too degenerate. So we're going to expect that when we look at higher strata, we're going to get worse singularities. Okay, and then for each d is the degree of the curve. So we have this parameter d, and that's kind of like a handle that we can turn. And for this construction to work, you need d to be big-ish, but it doesn't have to be that big. How big? I don't know. Somebody knows. Francis? Anybody? No.
No.
Yeah, it's not that big. Yeah, so for each degree, you get an instability stratification. I've called it HKKN, but that's the instability stratification of this locus. So every point in here corresponds to a curve, and I'm just stratifying it according to what is its worst co-character. So we want to understand what this looks like. What is this stratification? That's the question. And moreover, what happens as d goes to infinity, right? So this all depends on a parameter d, which is the degree of the curve. And the classical construction says if you take d large enough, then eventually semi-stability kind of always just means this. So is it true in some sense that if you take d large enough, this stratification sort of stabilizes in terms of it just has some intrinsic meaning depending on the geometry of the curve, and it doesn't depend on d. Okay, why would you expect this to happen? So this is motivation. If you're not a vector bundles person, it might not be the best motivation, but this is the motivation I was using. So there's another really important moduli problem in algebraic geometry. So arguably the other important problem, which is to classify vector bundles on, let's say, a compact Riemann surface, a smooth projective algebraic curve. And just like with curves, you have the same problem where the isomorphism classes could jump, meaning if you try to parameterize all of them in one space, that space is going to be horrible. So there's a notion of semi-stability, which you've either seen or you haven't, and if you haven't, then there is some notion of semi-stability. It doesn't really matter what it is, it's some slope condition. And there is a moduli space of semi-stable vector bundles. So you can construct a moduli space parameterizing these semi-stable guys, and this is an open condition, so this is almost all of them. And how do you get this moduli space? Well, using GIT, unsurprisingly. Okay, and then there's also an intrinsic measure of the failure of this semi-stable condition. I've got 5 minutes?
Yeah, because then we have 206 and it's 2.
Cool, that's fine. 5 minutes. So, yes, so if you have something which is not semi-stable, then you have something which violates the slope condition here. So you just take the thing that maximally violates it, quotient by that, and iterate. And this gives you a filtration by subbundles, which has some properties, and you can record the slopes of each of the subfunctions that you see. So this would just be a bunch of rational numbers. And this is some invariant, which is going to measure how unstable your vector bundle is. Okay, so now we've got 2 ways of measuring the instability of a vector bundle. We've got the GIT construction, which just indexes by worst co-characters, and we've got the Harder-Narasimhan type, which just is coming from the Harder-Narasimhan filtration I just mentioned. And you'd expect these would match up in some sense, and indeed they do. The sort of pithiest way to say they match up is that there is some stratification on the stack of vector bundles, which is equal to the co-limit of the HKKN stratification as some parameter gets very large. So the point of mentioning this is to say, in the case of curves, you've got this HKKN stratification, this instability stratification, which depends on D. Why on earth would you expect that it would stabilize as D gets large? And the only evidence at all, really, is that that happens for vector bundles, and it would be good if it did. So it's not really something you can experimentally verify, really. Okay, and then I'll just say, the fact that this is true for vector bundles meant that we could construct moduli spaces for unstable vector bundles. So this theorem here with Vicky is the kind of thing one would want for curves. And the first step towards classifying unstable curves is to understand this, the HKKN stratification for the curve convention. Okay, can we make all this work for curves? Okay, bad news is that stabilization of the semi-stable locus is not guaranteed. So, you know, there are examples where this just doesn't happen for pretty reasonable GIT problems. But okay, let's be optimistic. What would you have to do? You have to find the right maximal torus, and then for that maximal torus, you have to solve some proximum problem. Find the closest point lying on some polytope. Okay, but generic T does not contain a worst co-character. So if you pick a T at random with probability 0, will you get the right thing? And this is the thing that really makes life difficult. You want to send D to infinity, and the dimension of this polytope is going to go to infinity. The number of vertices is going to go to infinity exponentially. So computationally, you're in trouble really fast. Okay, so what we did was we said, okay, this seems really hard. Let's focus on a simpler case. And that's where these monomial curves come in. So if you fix a semigroup, a numerical semigroup, so a subset of the natural numbers closed under addition with finite complement, then you get a monomial curve, which is, you know, just parameterize it like this. Just take your semigroup elements up like that, up to some value D. The genus of the curve is the number of gaps, and this is called the semigroup of values. So you just look at which orders of vanishing do I have in my local ring at a singular point, and that gives me that gamma. So for example, if I take the semigroup generated by 2 and your favorite odd number, then I get a curve which is singular, has one singularity, and that locally looks like this. So you get a sort of higher order cusp. Okay, and then the theory that really saves us is that the vertices of this polytope that we're interested in correspond one-to-one with subsets of gamma 1 up to gamma r, the elements of the semigroup, but not including 0 or d. So this thing is combinatorially a hypercube. So we know what it is combinatorially. That's really easy. But that means it has of order 2 to the d vertices, which is unfortunate. So the number of vertices does grow exponentially, even for these incredibly simple curves, which are the simplest possible things you could try. So just to go back to the cuspidal cubic example, here the semigroup, you know, is 0, 2, 3, and we stop at 3 because it's degree 3. So it looks like this, and there should be 2 vertices because we can either take this element 2, or we can not take it. There's only 2 subsets we can take because we have to have the endpoints, and that corresponds to this vertex or this vertex, taking it or not taking it. So in this case, at least we can verify this this result of Kapranov, Sternfels, and Zelevinsky, which, by the way, is true for like toric varieties in any dimension. So I'm only using a very baby case. Okay, and then the proposition which makes this work is that we can turn this into a convex optimization problem. So if your co-character has these weights, you can draw the graph of the weights over the corresponding semigroup elements, and the proposition says that this thing that we want to maximize is equal to the area, not under the graph, but under the lower convex hull of the graph, the blue. So you have to take the slopes to be increasing. Yes, but they start out negative. So in particular, you know the worst co-character must itself have slopes increasing. And that's great, because that means the area is a linear function. So it's equal to the inner product with some vector A, and for example, a simple cusp y squared equals x cubed. What happens is you get 2, 3, 2, 2, 2, 2, 2, 2, 2, and then as you add more degree, you just get more 2s, and then you always have a 1 on the end. So we're looking for the closest vector to this vector, which has slopes increasing. That's the problem. Does the answer to that stabilize as d gets very, very large? And if you think about it, it must do. But it's really hard to prove, at least it's hard for us. Okay, and then this is the theorem which says exactly in what sense this thing does stabilize. Okay, so you have some bunch of corners, these weights are independent of d, then you have a final corner, and then the end you just get a least squares regression line. And as you increase d, this least squares regression line just gets longer, so you see no more corners. In particular, the curve that you get as a sort of associated graded when you take the limit is determined up to isomorphism independent of d. And then we can think, pretty sure, at least subject to some technical conditions, we can generalize this to curves that don't have a GM automorphism. And then I'll just show you kind of what the animation looks like. So this is for a simple cusp. You can see it's kind of, so what happens is it starts out straight, and then you get these two dots here. And then they're still both there, but you just can't see them because they're so close together. And the last thing I want to say is, the whole point of this really is to think about geometric genus. That should say greater than or equal to 2. So that's what we're going to do next, move on from rational curves to higher geometric genus. So I'll stop there. Thanks.
Thank you. So I would normally ask for questions, but I'm also mindful that it's 2:40 and the next talk starts at 3, and in between I have to get you all to have some tea and cake. So I was wondering, so we'll have maybe one quick question, and then any questions you can ask you there. Is that all right?
Yeah. So maybe a big question, but you had the moduli problem for curves and the moduli problem for vector bundles over curves, and you show that in some sense there is some equivalence. Is there a way to do this more constructively, like to have some equivalence of categories in some sense? So is it just like
I mean,
similar behavior?
Yeah, I mean, I think with hindsight, it was sort of 80% wishful thinking. I mean, when I had the idea to do this, I didn't know, for example, this result of Chen-Yang Xu, and that you're not guaranteed to get even the semi-stable locus isn't guaranteed to sort of stabilize if you take the parameters large enough. I didn't know that. So with hindsight, it was kind of a risky thing to do, and it was just something I hoped would happen. And I guess I still don't know that it does, but at least now we have really good evidence that it does in a decent number of simple cases. But yeah, I don't know of any way to kind of make that formal. It's purely just, oh, it works over here. Wouldn't it be great if it works over there?